Hi, Mark. I read, as you know, I read very carefully the chapter on transactional sagas of your book, Software Architecture, the Hard Part.
Oh, yes. Yep.
Yeah, it raised a lot of questions in my mind, and I thought that those questions would be interesting also for our audience. So I would like to ask them to you.
Yeah.
And so let's say that in your chapter you speak about atomic versus eventual consistency.
Oh, yes.
So an atomic saga is a saga that runs within the scope of an HTTP request. It starts and ends with the request. Even the compensations. I mean, if you have compensations because something goes wrong, the compensation itself is run within the scope of the HTTP request. Is that correct?
That is. So, we usually think of atomicity when we think of the traditional ACID transactions. The A is, of course, atomicity, which during the course of any given transaction, we continue to do updates on different tables. And we typically do a commit or a rollback. And we think about that atomic transaction as really meaning all or nothing. Well, the problem is, and you're correct, Christian, in a distributed architecture, if we, let's say, in a single HTTP request let's do something easy, like place an order. I have to go to an order placement service. Maybe I have to go to a payment service, an inventory management service, all these kind of different services within that same push of a button. And we, in fact, don't have true atomicity. Each of those services is doing independent commits to its data, to its tables or its database. So you're correct. What it really means when we talk about atomicity in a distributed transactional saga is really that all or nothing. And you're right, it's within the scope of a request. So in other words, because it's atomic, whether it's synchronous or asynchronous, I have to wait for all those actions to occur, all three of those actions, because it's all or nothing. If an error occurs, I have to wait until all those compensating updates occur. And that's really what we mean by atomicity in a distributed architecture.
Okay, thanks, Mark. It's a lot clearer now. And this introduces the next question, which is a question on the terminology. Because you used the term atomic consistency, and you just explained why it's a little bit different from the meaning it has in the context of a simple database transaction, because we are in a distributed system.
Yeah.
So my point is also eventual consistent sagas should be atomic, in the sense that they also have to enforce the fact that if something goes wrong, you have to compensate. Shouldn't it be better a term like immediate consistency?
Yeah, that's a really good point, Christian. As you know, naming things is really hard.
Yeah.
But yes, it really is immediate consistency versus eventual consistency. Exactly. Especially when we talk about error handling, because in eventual consistency, an error may occur, but I'm not going to make the user wait while we kind of repair everything in the data. And that means that it will eventually all be consistent, whether that be 10 milliseconds or a half a day.
Yeah.
But you are correct. Actually, here's a really good example when we talk about happy path. So all or nothing, atomic transaction. So let's use our example where we do have to place the order. So it gets inserted into an order table. We have to apply a payment and then adjust our inventory. So 3 actions when I hit that order button. Well, atomically, an atomic transaction would say that all 3 of those need to happen during that HTTP request. Again, irrespective of if they're synchronous or async. And this is where the definition really makes sense, is when we talk about async. Because if all of those actions are asynchronous, so I insert an order and I send an asynchronous request, let's say through messaging or a stream over to payment, and then an asynchronous request to adjust the inventory. Well, if we designate that has to be an atomic transaction, all or nothing, that means even though it's async, I have to wait. But with eventual consistency, because it's not atomic, what that would mean is once the order is inserted, because everything else is asynchronous, it responds immediately back to me and says, okay, your order's placed. We'll apply the payment and we'll adjust inventory at some point because it's not all or nothing. And so it further helps that definition when we even think about asynchronous communications.
Okay, thanks. Thank you very much. So, next question. In an atomic saga, in the sense of the previous question, I mean, we just defined what is an atomic saga. We just defined that. So, in an atomic saga, and there are no retriable steps. In the sense that you cannot just think that something will eventually be consistent because you are in an atomic saga. Therefore, atomic sagas require compensation at each step. Is that correct?
It is. And now this, Christian, is where it gets difficult, because you're right. When we talk about atomic transactions, or what we really should say is, I like your term, immediate consistency, means that during that request, what we're doing really, Christian, is simulating a commit and rollback against data sources and or just one data source, but multiple services that are distributed. And so we're trying to simulate the same thing that we get with traditional ACID commits and rollbacks, which brings an interesting point. So the answer is yes. In that regard, we do have to issue compensating updates to reverse a payment, to add the inventory back in, to delete the order, so that when we say, whoops, an error occurred, from the user's standpoint on that single HTTP request, all the data is back to normal. However, here's where it gets fun. So, Christian, I'm sure you're familiar with the 8 fallacies of distributed computing.
Yeah.
These were 8 fallacies back in the 90s that were coined by Peter Deutsch and some other folks from Sun Microsystems. Well, Neil Ford and I have been working very hard to coin the next 8 fallacies of distributed computing. And we have 2 so far that we've published. But it's interesting. Fallacy number 10 of distributed computing: compensating updates always work. You see, now we say, oh, sure, just issue compensating updates to reverse all this stuff and everything will be fine. But what happens if those compensating updates fail? You see, a fallacy is something we believe to be true. And we always believe that those compensating updates will in fact work. So imagine if we tried to reverse the payment in this little chain and that failed. What do? Because now we're in an inconsistent state, but we are required to have an atomic transaction. And so this adds a significant level of complexity. So in these kind of situations, that's where a retry may in fact occur, to say, whoops, that's weird. The payment service is non-responsive. Or let me keep trying, because I have to hold up that request until everything is consistent. And this is where exactly trying to simulate atomic transactions does in fact break down. So it becomes extremely complicated to deal with these situations. And in a lot of cases, if a compensating update fails, we really only have one choice, and that's to push an error up to the user and convert to eventual consistency, because there's no other action we can really take. So this is where in fact things fall apart when we try to simulate atomic transactions in a distributed architecture. One of the interesting things, though, Christian, to kind of address some of these complexities is to manage data through state rather than try to do compensating updates. And this is a technique also shares a lot of complexity, but each datum or the context of the request itself carries state with it. And in our example, that state would be various things, whether it's ordered, whether it's paid for, whether the inventory is adjusted, or whether it's been completed or placed. Well, it doesn't matter what state that request is in. If it's not at the end state, like placed, then that data is not accessible to anybody, which helps simulate isolation, but also which means we can now do retries on that. So it's almost like a balance between eventual consistency and atomic transactions, kind of address this retry problem. But there are retries, but the problem is you can't retry until everything is in a consistent state again. Yeah. So state management, in fact, does help address that issue by saying, well, we're not going to rely on compensating updates. It's a lot faster, a little more reliable, and now we have retry capability because we can fast forward over to where we were at because we happen to know the state of each of those data items. So,
I see.
Yeah.
That there is a lot of more questions, but yes, because it's. But well, I'm interested in another aspect. How are failures in the orchestrator itself handled in the case of Atomic Saga?
Mm-hmm. So you're right. When we look at the two, so out of the 8 sagas, 4 of them happen to be orchestrated or using an orchestrator, and the other half are choreography. So if the orchestrator fails, that becomes architecturally a single point of failure. So typically that is addressed through multiple instances of the orchestrator itself. But it's interesting, that requires that the state of that request, where we're at in that, be persisted somewhere, or preferably persisted, and or that state shared through maybe in-memory replicated caching between those instances, so that any given request ID coming in we may have 6 instances of the orchestrator, and they all those instances know that for request 1, 2, 3, this is the current action being taken. And so if we lose an instance, another one can pick up that request and continue where it left off. And that's pretty typical for errors actually within the orchestrator itself. But Christian, this is a great point, a great question, because what it really shows is the role of that orchestrator. And when we talk about orchestration of a request, that orchestration service really only acts as a mediator. So its only responsibility is to provide error handling capabilities, to know the state machine, which requests need to be done next, if they can be done in parallel or if they have to be done serially, which ones are async, which ones are synchronous. But that's it. In other words, and also there's one other role, which is that contract aggregation, because each individual service has its own contract. It's communicating to that orchestrator. But when we talk about the single HTTP request coming into that orchestrator, that's a contract with the user interface. So that would be a third role of that orchestrator, is to basically own that contract and aggregate all that information coming to then send it to the user. But the key point is that's all it does. Unlike traditional service-oriented architecture, SOA, where we had these big enterprise service buses that just did everything in the world. So they don't contain business logic, which makes them a lot simpler, easier for another instance to pick up and continue where it left off.
But I have a doubt on this. I mean, how technically, I'm afraid to go too much low level, but how do you share the same request, the same connection between 2 instances of the orchestrator? I mean, put in a case in which the orchestrator instance A falls down during the request. Do you know any tool or any technique for which the instance B of the orchestrator takes the request and go on processing the request?
Yeah. So generally, that kind of model where we would have multiple instances of that orchestrator would require some sort of load balancer that we're actually talking to. So the request would actually go through a load balancer, which would then direct to each of those instances of the service. For example, tools like Kubernetes, any kind of service orchestrator handle that handoff. If one service ends up failing, it will transfer that request to another instance. A lot of cases, especially in microservices, it actually is amazing. Errors are occurring all the time. Because of the fine-grained nature of those services, the mean time to recovery is usually measured in hundreds of milliseconds. So a lot of times that recovery is so fast that we don't even notice that it's happening, that a service instance did go down. Basic load balancing or service orchestration tools are how that kind of mechanism transfers. That would be really hard if we were doing a direct RESTful point-to-point call with a single instance. If that instance goes down, that's what the request is tied to. It would require those kind of tools, a service orchestrator like Kubernetes or a load balancer to be able to redirect.
Well, I suppose also, but it's just an assumption I'm making now, and we have to prove it, that each step in this saga, in this atomic saga, each step maybe should be idempotent, because if the same request is retried, do you agree on this?
Right. So now this is where specifically these kind of, and I don't even want to call them edge cases, because these can happen. So the error handling part of the orchestrator is the complex part. You're right, the idempotency. Because if I'm in middle of applying a payment, an orchestration service goes down. Another instance will pick that request up, know that it's in the process of making a payment, but now we have to deal with whether to reapply that payment, to check to see first if that payment has been finished. That's where a lot of the complexity lies. And the implementation of that really depends a lot on the type of protocol, whether it's async or synchronous type of protocol, and whether to do a check first and then a retry. So that error handling, when we kind of pick up that request in the middle of a saga, we know the state, but we're not sure what is happening in that state necessarily. So this is where the complexity of the error handling part makes it really, really complicated especially on a handoff piece. Yeah,
I see. Thanks a lot, Mark.
Yeah. Now, these are really complex scenarios, Christian. Another model, if that orchestrator does go down, is to basically just do a retry from the start instead of that handoff, so that the request is basically retried. We know the state, so we kind of have a similar problem where the new request comes in, but because we know the state, we know where we were at, but not whether that's completed or not. And so, orchestration failures are quite catastrophic in a transactional saga. Absolutely.
Yeah, that's why maybe it's a better idea to use what you call the fairy tale saga, because in that case, compensation update may be executed after the scope of the request. So we can think as the compensations themselves as retryable.
Yeah.
But the problem with the fairy tale saga, and this is my question, is with the management of HTTP connection.
Yeah.
Because if it's orchestrated, the orchestration has to be aware of the open connection and close it, send a response, and then execute the compensating update.
Correct. Yeah.
Yeah. Okay.
And in a lot of cases, I mean, there's so many different kinds of implementations for that, ways of implementing that. One way is, of course, you're ending that HTTP request. You're sending back the 200 saying, yep, we're done, but I'm going to continue on some other things. And that continuation can typically be done through threads, for example, so that request is officially ended, but the orchestrator is still working on that particular request. So threading is a very common way of actually managing that, whether it be synchronous or asynchronous in that regard.
Okay, thanks.
Yeah.
Thanks a lot. So this is, I think, an interesting question for you, because I know that you like very, very much the concept of hybrids.
Oh, yeah.
So my question is, in general, so my question is the possible hybrids between, for example, Saga, orchestrated, and choreographed for our restaurant, for our example of orders and payments.
Okay, so interesting. The hybrid piece, there's two answers to that question about hybrids. First of all, we get a lot of questions when we start to introduce these transactional sagas about, well, but I have some things in my system that are sync and async, and I have some things that are orchestrated and choreographed, and I have a few things that I need to make sure these two tables are atomic, but not all the others. And so we start getting all these weird combinations. So the first part of the answer is, and this is going to be difficult on a kind of a podcast answer, but I'll explain it as well as I can, is those transactional sagas are associated usually with what's called an architectural quantum. In other words, a separately deployed independent part of the system that can act independently from another part of the system. Basically, this is where the architecture characteristics of scalability, elasticity, fault tolerance all live within a quantum. Think of the architectural quantum as a kind of an independent, separate part of the processing and the processing flow. Well, with that means that we can start combining different parts of a system with different transactional sagas. So an entire system doesn't all have to be the parallel saga or the fairy tale saga. Some requests in our system may be orchestrated. Some may be choreographed. Some requests we may be able to do async and some synchronous. Now, within a portion of the system, the single quantum, basically you can say, well, we're using the parallel saga, but we also have synchronous requests within there too. So we're kind of mixing up sync and async. So generally, how we address that hybrid question is you may have a particular saga. Let's say it's orchestrated using synchronous. That would be the fairy tale. But some of those requests are asynchronous. So would it still be the fairy tale saga, which means it's eventual consistency, it's synchronous communication, and orchestration. So what we look at in those hybrids is what is the core processing viewpoint from the user's perspective. So, for example, maybe some of the calls to the services are async, but the primary pieces are synchronous. So from the user's perspective, I have to wait for things to happen. In that case, it would be synchronous saga with some async kind of mixed in with it. Versus the parallel saga, which is orchestrated, eventual consistency, but everything's asynchronous. So from the user's perspective, I don't have to wait for anything. But maybe some of those requests require a particular ordering, which may be synchronous. But from the user's perspective, I don't wait for those. Therefore, it would align with the parallel saga. So it does get confusing when you look at some systems and you say, I can't tell what saga this is because it's all mixed up. But what we try to urge is to look at what is the main processing. Is it primarily orchestrated, primarily synchronous, with a little bit of async sprinkled in, or the other way around? And that's how we kind of align with a particular saga to get, again, the characteristics of those.
And thanks. Thanks a lot. So next, in Saga that are choreographed and also synchronous. Mm-hmm. So like what you call the time travel saga, for example, which is choreographed, but the communication is synchronous. Yeah. There's I think, in my opinion, there's an unmentioned coupling that I see. The services has to be aware of the next service involved in the saga. Right. Because, yes. And isn't this a high price to pay in terms of coupling? I mean, is it worth it? You know?
Yeah. So it's interesting. Yeah. So the time travel saga is one that is eventual. No, I'm sorry. It's atomic transactions for the time travel, but it is synchronous choreography, which might seem a little counterproductive. It's very similar to the pipeline architectural style, or what's sometimes referred to as pipes and filters. ETL processes do this. Maybe it's a transformation, but it's all one unit of work. It's not common, the time travel. But let's answer your question about coupling, because each service does need to know the next call in the chain, but that's all they need to know. They don't need to know about any of the other services. And so there is, so from a pure service to service coupling, it's not as bad as orchestration, which if we have 10 services, the orchestrator has to know about all 10, and all 10 have to know about the orchestrator. But here, each service only knows about its neighbor. That's it.
Yeah, I see.
So, but it's it's an interesting question though, Christian, because so there's two types of coupling. From an implementation coupling standpoint, the coupling is fairly low, but semantic coupling is high. So let me explain what I mean. If we were to do a tool, take any sort of tool and look at afferent and efferent coupling, it wouldn't be bad because each service is only tied to one other service. But because it's atomic, all those services are needed in order to do that request, which means semantically, not syntactically, but semantically, all of those services are coupled to that request. So it's really interesting. It kind of is how we define coupling. So yes, there is semantically a high degree of coupling in something like the time travel saga, where we're building synchronous between all of these services. It's kind of, let's take our order example. We don't want to use orchestration, so we use choreography. But all those three actions need to occur before we can send the request back. Place an order, make a payment, and adjust the inventory. Well, so now we've got a synchronous chain from order placement saying, okay, payment, go do your thing. And I'm just going to sit here and wait. And then payment directs it over to inventory management. Inventory does its thing. And then finally ends the chain by talking back to order placement. That would be a very typical example of that kind of request. Now, the problem occurs on errors. When we come back to the error handling, Christian, because what happens in these sagas is we now have to actually reverse that chain. So interesting, when we talk about coupling, it doubles the coupling. Because if I have to reverse the chain, that means I need to know about my forward neighbor, but I also need to know about my previous neighbor.
Yes.
And so coupling actually doubles when we start talking about error handling. So it's a really good, keen observation you made about coupling in that synchronous choreography kind of model. Again, not very popular. It's not used a lot for these kind of
and it has consequences on what you call the architecture quantum.
It forms a quantum of one, exactly, because of that synchronous dynamic coupling between all of those. Yeah. So it's not a very desirable kind of architecture or transactional saga. But like a pipeline architecture, the kind of example I gave would be those. Now, to make it so to improve that situation significantly, we use eventual consistency, and that means any error on the chain, we just immediately respond back to the user, and so we don't have to necessarily reverse the well, we still have to do compensating updates eventually, but we have a lot of other options aside from synchronously reversing the chain through. One of those being event-based eventual consistency, where any given error that occurs, that particular service just triggers an event that says, hey, I failed. And then all the other services in the chain respond to that event and just reverse whatever they did. So yeah, removing the atomic piece from that is pretty significant when we're talking about choreography. Yeah.
Okay, thanks. Maybe I was thinking while you were talking that maybe we could have a pipe filter architecture which is not based upon HTTP. So and then in some way lower that coupling that makes the architecture quantum greater.
Yeah, exactly. Yes. Yeah. Precisely. Yep. As a matter of fact, if I love this part about talking about the choreography piece, because one of the most significant pieces is, in fact, what we call the horror story. And the horror story is the worst possible combination of the forces we can have. And to give you a really good example, the horror story is atomic. It's choreography, but it's async.
Synchron.
Yeah. But because it's atomic, and this is what I was describing earlier in the discussion, because it's async, we still have to wait because it's atomic. So whether it's happy path or errors, that's why we named it the horror story. It is the three hardest possible combinations, but by trying to make things faster, by making it async, because it's an atomic transaction, we actually reverse that. We actually make it less performant. So yeah, this is one of the, I guess we call it one of the proofs of our theory, that these three forces are truly cojoined. That you can't just take something that's synchronous, make it async to make it faster, because it's not the async that's the problem. It's the fact it's an atomic transaction, which makes it too slow. So yeah, this is part of that discovery. Yeah, exactly. Yeah.
So then come my favorite question. I'm very interested into your answer here. What implementation is recommended for sagas in Java? For example, Apache Camel. Apache Camel.
Yep. Yeah. So the sagas themselves are like patterns. These are ways in which the design, the overall architecture of those three forces interact. So they can be implemented in many different ways. However, my favorite does in fact happen to be Apache Camel.
Wow.
Every person has their own kind of favorite tool or whatnot.
Yeah.
But there's, excuse me, there's a host of platforms and tools that we can use to implement any of these sagas. Mule is one, certainly Spring Boot. Camel happens to be my favorite because from a development standpoint, I find the API, I find the use of it very simple. It's very straightforward, very easy to use. And the best part of all, and let me see if I have the book here, is... Yes, I do. So this is, of course, the Bible, Gregor Hope and Bobby Wolf's book, EIP, the Integration Patterns book. The reason why I also like Camel and appreciate it so much is that if you open up any given pattern in this book, there is an API call, a method within Apache Camel, within its DSL, that mimics it directly. And so it is the closest match between the three major players that I just mentioned that I have found that matches almost directly to this book. And so any kind of pattern that you see from integration standpoint to implement these sagas, it's very intuitive and fairly easy to use. I like the DSL of Camel, Apache Camel. I find it just very powerful and very, very useful. Also, very extensible. So a lot of times we end up with all these kind of tools, Christian, with the 10% trap. All these DSLs, all these things work very nicely to get you 90% there. And then it's that last 10% that all of a sudden is near impossible to implement. 4GL's had this problem with the last 10% trap. We can put together a website in a day and a half, but then the users say, yeah, but I don't like that widget. I want to replace it with this image, and I don't like the button over there. Can you move it over here? Yeah. And after 4 months, you finally get it done. These tools are no exception to that as well. But I do find and appreciate that with Apache Camel, it's very extensible. So it minimizes the effort for that last 10% trap. Any of these can work very nicely with, especially, Christian, the first 4 sagas that we have in the book, which are all the orchestrated sagas. I actually, in the book, I can't remember the order in which we put them in. But now now that we do kind of the training classes and stuff, we put them in order of starting with orchestrated and then move to choreography. It just kind of, that ordering made a little more sense.
Yes.
There. But particularly for the orchestrated sagas, that actually is my favorite in the Java platform to actually implement.
I mean, I totally agree with you. Actually, I very like the implementation of Apache Camel. The good part is that it's totally decoupled from the model of the persistence you have. For example, event-driven RAM is quite coupled with how do you use your persistence. So it enforces a little bit the event sourcing part. But if you are not interested into event sourcing, but you still want to implement a Saga, I think that Apache Camel is a very good choice. It has a defect, maybe it's just transitional. It's about the fact that there's just one single instance of the Saga coordinator, which is Narayana.
Yeah.
And there's no way today. There's no way currently to have Narayana in a HA higher availability deployment.
Right.
So maybe this is the only pain point that the implementation has.
Yeah. And it's a lot of those trade-offs of the fault tolerance for the simplicity and the performance and speed of use or ease of use. That's one of the trade-offs that a lot of times I will use the old cost-benefit analysis method, CBAM. When we talk about some of the trade-off analysis techniques, ATAM, which is the architecture trade-off analysis method, and CBAM, cost-benefit analysis. So we trade off between opposing forces in architecture, performance or scalability, performance or security, which is one of the more famous kind of trade-offs. That's what ATAM's really good for. Or to say, I can give you a lot of this, but not so much of this. But then we get into, yes, but we need high fault tolerance. So we need multiple instances of our orchestrator. Oh dear. So we have just increased the complexity of our system tenfold, literally. And so that's where the cost-benefit analysis method, CBAM, really pays off. Because we can say, sure, we can do that, but now we're trading off against ease of use, complexity, and most importantly, cost. That's going to take a lot of effort and be fairly costly to add that in. And now we have to determine whether the cost and effort is worth the complexity of the infrastructure and error handling to actually have multiple instances of our single point of failure. Of late, a lot of the modern ATAM practices have actually now bridged these two methodologies together instead of having them treating them separately, putting them together so that when we start doing our trade-off analysis and determining priorities and which characteristics are most important, we do take feasibility, that cost and effort and time into account as well in that. A lot of this, Christian, is related to something I really love, which is from Sun Tzu's Art of War. And that is divide and conquer. So I'm faced with this a lot at client sites where we need high availability, or maybe we need really high fault tolerance. And it's overwhelming. It's going to really derail this project. So then I ask, well, wait a minute. Do all parts of the system need high availability? Do all parts need high fault tolerance? And Sun Tzu in his Art of War book said, if his forces are united, divide. And it is something we just don't think about. When we get requirements like this, operational requirements from our stakeholders or from operations, we tend to think that the whole system needs high scalability, high performance. And if we start to really look, it's not true in a lot of cases. And this helps simplify the effort and the cost associated with trying to implement these kind of things. So yeah, it's a great tip to remember: divide and conquer.
Yes. Well, in this specific case, I think I thought a little bit about this. The problem is when the coordinator goes down, every saga that is running in that moment is going to fail. So the problem is quite massive in my quite massive. Yeah. So. Okay, so Mark, I don't have any more questions. So I think that your answers are very full of concepts, and so we have a lot of concepts to reason about after this.
So kind of to kind of put a maybe a little summary on this.
Yes, please.
The idea of these transactional sagas was really an observation that we made, Neil Ford and I made during the writing of that book, kind of towards the end of the writing, that these three forces that we're talking about, whether it's atomic or eventual consistency, whether it's orchestration or choreography, whether it's sync or async, are in fact co-joined. And we realized that we tend to make decisions on these different forces independent from the other. And we've had too many experiences where teams will do the right thing and say, for example, oh, we need to make this faster. Let's do async. And it turns out that it doesn't make it faster, but makes things more complicated, and it destroys scalability. And so the fact of, we hear a lot, and you'll read a lot in a lot of articles, orchestration is bad. Don't do it in microservices. And these are from people who have had really bad experiences with orchestration. But it's not orchestration's fault. It's the combination of doing sync or async and atomic or eventual that causes orchestration to be bad. Because we could easily demonstrate 4 to 5 star ratings, which means great responsiveness, great scalability, low coupling, and simplicity, the complexity rating, by using orchestration. So, these are the kind of things that we tried to do in this idea of these transactional sagas. I would not call these necessarily recipes, but they are patterns. And if you take these 3 forces and each has a binary, it does form all 8 of these. So there are 8 possible ways of combining these forces. A funny anecdote to close with here is Neil and I, when we were modeling these, said, well, some of these are theoretical. Like, no one would do these, in particular the horror story. So we said, well, let's put the pattern out there, but it's not, it's probably an anti-pattern. So we figured some of these would fall off. Well, we started to look, and with the exception of the horror story, Neil and I combined have seen all of these in the wild. Exactly 2 months after we coined the horror story, Neil was at a client and they handed him the horror story. Neil texted me and he said, Mark, that's our 8th one. We have found it in the wild. So it turns out that all of these we have seen. So they are not theoretical. But
they are for real. Yeah.
This is good. Could you look at the horror story and somebody would say, why would anybody ever do that? And it was a response to make things faster, do async. But they ignored the other 2 forces. And that's what caused things to completely fall apart. So it was, so these are an effort to help really simplify the decision-making and realize through those star ratings that we had in the book, what happens if I use these combinations? And I can actually see scalability is not going to be great, responsiveness won't be good, and it's high coupling. That's not what we really want. And so it saves a lot of time finding these things out after the implementation.
Yeah.
So
maybe we can say that the bottom line is that your analysis on the 3 axes, the whether orchestrated or choreography, whether it's atomic or eventual consistent, and whether sync or async are the way we should, or we as architects should study every case of Saga. Okay.
Yeah, exactly. And that's really the purpose of putting those in the book. Now, eventually, Christian, when we do the 2nd edition of Software Architecture, the Hard Parts, we will be diving into some of the details we actually talked about on this call here, just because we added these towards the tail end of that book. We were already at our page limit, and so we weren't able to really dive into those as much as we wanted to. It is one area that both Neil and I agreed we need to greatly expand the details of in that to address some of the things like error handling and some of the complexities of the reasoning of why the star ratings are the way they are. So that will be something that will definitely be expanding in the 2nd edition.
yes, maybe because I'm really happy of this, basically because there are a lot of need for clarification in the field of sagas, because there's a lot of projects that we see that they need to implement sagas, and actually there's a little literature on them. So so I'm very happy you will put your effort in the new chapter and the new book.
Well, and also, Christian, what we kind of are hoping to do is offer software developers and architects a helpful negotiation tool. And here's what I mean. So the business stakeholder says to you, we have to have atomic transactions. It's got to be all or nothing. Data integrity is that important to us. Well, so what do? We respond and say, okay, and but now, and we try to do it, which doesn't work well. But now we have star ratings and a consolidated chart so that we can have an architect say to that business stakeholder, well, sure, we can do that, but let me show you the implications and trade-offs of doing so. If we made it atomic, and we can look across all 4 sagas, it's going to sacrifice responsiveness, scalability, complexity, and coupling. And so those are going to be our big challenges. And this gives us a way. See, a lot of times what we have observed, Christian, is business stakeholders will say, make it atomic, but they don't understand what the trade-offs are. And a lot of times, neither does the architect until it's too late. This way, now, it's a negotiation tool to say, let me show you what the implications of your decision are. And do you still want to sacrifice all 4 of these things to have that atomic simulated transaction? And in many cases, it will be, no, we need high responsiveness. And now we have a vehicle for discussions. And that's a really powerful aspect of these sagas, is to be able to see firsthand, without implementing it, what the trade-offs are. And the biggest trade-off is, in fact, atomic transactions. If you look at the chart, it is the one that impacts all 4 of those criteria the most. So it just gives us a way of saying, look, if we move to eventual consistency, we can increase scalability, responsiveness, agility, time to market, all of those things. So, yeah. So that's our hope, is it does become a tool and a vehicle for that.
It will, I'm sure. So, Mark, I think that we are a little bit running out of time. So I thank you very much for your answers. I promise I will read about them a lot because they are very good. I hope we can repeat some sessions like this upon other topics or something like that.
I'd love to. Yeah. And your questions, Christian, were fantastic. I mean, these are clarifications that we weren't able to put in the book. So I think this is going to be really helpful for the industry as a whole.
Wow. Thanks. So I will keep on asking them.
Definitely. Yes.
So thanks a lot, Mark, and see you next time. So
all right. Okay. Bye-bye, Christian.
Bye. Thanks.